Hello everyone, I'm very delighted to be here. Thanks Siva, Anita for calling me here. So I was here for the last version of this summer school also, and I had a really good time. So let's hope that this time also we interact a bit and have some fun with this talk. I think you've been bombarded with a lot of math, so let's keep things a bit light for now. I'll be talking about theoretical computer science. That is my area of research. And without really going into details of the area of research, I would like to just convey my excitement, my enthusiasm, and in general, the enthusiasm of this field to you. And in this talk, I would like to bring the two areas slightly together. You have the math background, I am a computer scientist, but sometimes the tools we use could be very similar. So I just want to, through this talk, also convey that for somebody who has had a math background, you may pursue a degree in mathematics, but at later point, like the talk we just saw, you may end up pursuing computer science or any other area of current excitement in any research field, and mathematics could be useful. So mathematics is extremely fundamental for big discoveries in theoretical computer science as well. So I just want to convey these basic ideas through my talk, and I hope they come across in the next 1 hour or so. Feel free to stop me anytime, feel free to ask questions, and I'll also be asking some questions, so it would be great if you answer some of them. All right, so let's get started. What I'm going to do in this talk is I'll present 3 puzzles, and each puzzle is intended to convey one basic idea, but primarily we'll be solving the puzzle. So once we solve the puzzle, and the puzzles are quite simple actually, then eventually we'll come to the idea that the puzzle conveys. And typically the theme of every puzzle involves discrete mathematics, which is sort of kind of things that Suresh was talking about, arithmetic over F2 or finite fields or things which are finite in general. Yeah. Unlike the analysis or other things that you may be learning over here, which require thinking about continuous domains or so on. So we are thinking about finite discrete objects. And we'll also argue about what are very natural concepts to any human being, which are algorithms. Algorithm is nothing but a set of instructions for somebody else to perform that task. Yeah, it's a tool for a lazy person, basically. So we'll just talk about these 2 things. So let's get started. The first puzzle. Okay, so the main characters of a puzzle are Akbar and Birbal. And this is a puzzle about some closed rooms. So here's the story. There is a poor farmer that comes to Akbar asking for some loan. Akbar is very generous, but slightly witty. So he says, yeah, be my guest, take whatever you want. But there are some rules. All right, so what are the rules? The rules are very simple. There are 100 rooms numbered 1 to 100. Now, there is one room among them which contains 100 gold coins. Except we don't know what that room number is. So the farmer doesn't know what that room number is. Let's say X. The condition is if you open a door labeled anything, so if you open the door labeled X, you just take the $100, the 100 gold coins, they are yours. On the other hand, if you open any room which is labeled less than the actual door number, then you have to pay 1 gold coin to the king, to Akbar. Okay, so you lose 1 gold coin. Obviously, if you don't have anything to start with, you keep it as a loan, and then once you get the $100, you can pay out of it. Right? On the other hand, if you open a door more than the numbered door, then in fact that's terrible for you. You have to pay 40 gold coins to the king. So you better not open a door numbered higher than that too many times. Obviously, the main problem is farmer does not know what this X is. Okay? So the puzzle is, what is the maximum number of gold coins that the farmer can take home? Is the puzzle clear to everybody? That's the puzzle. Any attempts? Every time you open a door which is labeled less than the actual one, you pay 1 gold coin. Yeah. So if you say open a door which is labeled more than X 5 times, you actually will owe Akbar 40 times 5, that is 200 gold coins. So basically farmer will go home with a loan of 100 more gold coins. He came with no loan at all, and he'll go home with extra 100 gold coins loan on his head. So this is a situation he wants to avoid. It's not about how many times he can open a particular door, but how many times can you open the right kind of doors, the wrong kind of doors, and so on. So let's look at the very first, very simple strategy, right? You can go home, the farmer can very trivially go home with at least 1 gold coin. Why is that? Just start opening doors from 1. Open door number 1, door number 2, etc., etc., etc. In the worst case, statistically, Akbar would have hidden all the gold coins behind door number 100. In which case, he would have had a loan of 99 gold coins. He would have received 100 gold coins after opening the last door. So he'll take 1 and give 99 to Akbar and go home. So at least 1 is doable. Okay? So while arguing about this particular very simple strategy, we assumed that the gold coins which we are after could be in the worst possible position. Yeah? In algorithm design, this is usually called as the worst case analysis of an algorithm. Yeah? So you don't know what inputs are going to come, but the inputs could be the worst possible inputs. Even in that case, you want your algorithms to work, right? So this is like the worst case analysis that we are trying to perform right now. Okay, so 1 gold coin is fine, but I mean, you're going there to ask for money, going back with 1 gold coin is slightly embarrassing, right? So can he do better? Can he go back with at least 10 gold coins? Is there some other strategy that you can devise? Maybe not 10, you might come up with some other strategy that may give some other answer. Fantastic, right? So what is being suggested is open the middle door, 50th door, okay? Now there are 2 situations that can happen. Either the gold coins are after the door number 50, in which case he'll only lose 1, and then he can just go sequentially into the second half, thereby losing, in the worst case, 49. So 49 plus 1, he would have lost 50 in this situation. But the bad situation is he opens the door 50 but realizes that he has to pay 40 at this point. What that means is the gold coins are in door number 1 to 49. In this situation, he'll end up paying another 48. Yeah? So he's paid 40 first for opening door number 50, another 48, yeah, which is 88, but he would have gone back with 12. Yeah? So fantastic, that's exactly what I was going to say as well. Okay? So is this the best that the farmer could do? Repeatedly do this, right? So how should we repeat it? Should we do 50 and then 25, 25 and then something else, something else? So let's try to work it out. If I do 50, then a 25 and then a 12, yeah? Right, so that's a bit of a problematic thing. In fact, the way the number of coins the kind of coins I'm willing to pay, I have to lose 40 every time I open a door which is large numbered, right? So that is a bit of a sticky point. This strategy, the second advanced strategy that one of you is trying to suggest is not quite going to work, because this may, in the space of 100, ask you to open a certain door 3 times, yeah, which is numbered higher than the actual one. And this is problematic, right? So that's not the right strategy. But let's not lose everything at this point, right? We thought that dividing it into parts is going to help. But it was not clear why dividing it into halves is going to be great. Maybe that's not the right way to proceed. So is there some other strategy that you can apply? So here, yes. 4 or 5 equal parts, great.
And then begin from the lowest number.
Right.
That will reduce the probability of getting a higher.
Right. So probability is not the right word because we are all doing everything very deterministically. But you're kind of right. So what is being suggested is just that instead of breaking it into half, etc., break it up into chunks of about equal size. Yeah, or some 5 chunks. If I divide it into 5 chunks, then I have around 20, etc. Right? So I open the 20th, then I open the 40th, and then her strategy is start from the lowest one. So you end up paying 40 only once, and then go into the range where you actually ended up paying 40 and zoom into that range. Right? So suppose we did it for 20, then I'll first open the door 20, lose 1 coin, 40, lose another coin, 60, lose another coin, 80, lose yet another coin, and then finally it could be in this last range, in which case I will lose 81, 82 for each one of the doors up to 99, 19 more coins. So 19 plus 4 more coins, something like that. Yeah, so you can do slightly better. Yeah, this idea is going to work, except we needn't break it up into 20. 20 is a very arbitrary number. Let's try to optimize this. Yeah, so there are 2 things. There are L intervals, and each interval is of length n by L, where n is the total number, right? And now we want to optimize these numbers. So for this particular puzzle, let's just do this. Okay, divide it into 10 parts of 10 each, because 100 is kind of 10 square and, nicely divided into nice sized parts and nice number of nice parts, right? So if we did this, let's just quickly do let's see how much one can take home. And you would see that, as we just saw, 10 to 80 you would end up paying 8 gold coins. And so 8 coins for 10 to 80. For 90, probably you will end up paying 40 more gold coins. Right? So 40 plus 8, 48. And then 10 more, 9 more. For opening, 8 more for opening 81, 82, etc. up to 88. So overall, you will end up paying 56, earn 100, so your total profit would be 44. Now this is slightly more respectable. Yeah? Can we do better than this? Okay, I like the confidence, yes. So we can. Can we? The 20 calculation that I did on the back of the envelope calculation was not quite correct, right? Because when I opened the door number 80, I could be paying 40 more. Because, it was between 60 to 80. So that was a little bit of a mistake I made. But can we do anything better? So, okay, fine. So before going into whether we can do anything better, let's just try to understand this strategy slightly better. Okay, let's just understand this strategy a bit better. And actually, let me present to you a slightly more realistic situation where a question like this may come up. Akbar, Birbal is all right. I mean, they don't exist anymore, unfortunately or fortunately. But such problems may come up even today. For example, you have a contiguous memory cell, array of memory cells, and one of them is defective. And you don't know which one it is. Okay? And if you probe any section of the contiguous cells, which is after this defective one, the system just shuts down. Okay? So, in an array of n memory cells, there is a cell k such that all cells from k plus 1 to n are defective. The processor does not know k. Every time it accesses a defective cell, the system just crashes, right? Find K with at most 2 system crashes. Yeah? Can you find what that K is with at most 2 system crashes? That's exactly the puzzle we just solved, right? 40, 100, all these numbers were so designed that you couldn't have done more than 2 mistakes in some sense, right? So this is really an incarnation of the same puzzle. Yeah, this looks a little more realistic to some, I guess, right? And as I said, to analyze this particular strategy that we designed, what we said was the cells must be divided into n blocks of size n by L each. Now, we know that at most L minus 1 probes will suffice to find the block in which this bad K appears. Yeah? Just go up to L minus 1. And at most n by L minus 1 probes will suffice to find exact location of this K inside that block. Yeah? Because the size of the block is n minus L. So you require at most n by L minus 1 many probes. So together we require L plus n by L minus 2 many probes. Now, how does one optimize this function? This you would have seen umpteen number of times, right? What is the optimal value of L which minimizes this particular quantity? That's square root L. That's precisely what we did. Right? We took this strategy for n equal to 100, figured out L should have been square root 100, which is 10. That's it. Yeah? So that's the abstracted out strategy for our problem, right? And we saw that these many probes are enough. So we were not actually, so the arithmetic won't work out to, the number of probes were not the quantity we were optimizing, right? Because the last probe which is bad was going to cost us 40. So this may look like a very simple puzzle, which obviously it is, but you may want to think about a few problems related to this puzzle which are not that immediate. So think about them. If you find solutions for them, write to me if you want, and if not, don't get discouraged. So the question I earlier posed for you, can you do better than this? Okay. So suppose n, L, n, k, etc. are parameters, and I'm asking you, can you detect this bad k in number of probes strictly less than 2 times square root n minus 1? Okay. And actually, the answer to this question is no. Okay. This strategy is optimal. Okay. But how does one prove that? Yeah? How does one provably show that this strategy is optimal? And this sort of thinking in algorithms is called proving lower bounds. Yeah? So what does proving lower bounds mean? You might come up with an algorithm to sort n elements, and that may take n log n time. Somebody else may come up with an algorithm that takes n square time. Looking at the two, you can obviously say the one that takes n log n is better. But if I turn the question around and ask you, can anybody come up with an algorithm that takes time less than n log n? Now that's a lower bound question. It's not about whether she comes up with it or she comes up with it. It's about whether anybody, any sentient being can come up with an algorithm that uses time less than n log n. And you know, it's not that easy to answer such questions because we understand so little about computation. To argue about computation itself is a difficult task. So for a general model of computation, it's not even known that sorting must take n log n time. If you make the model of computation to be comparisons, yeah, so how many comparisons are required to sort an array of n elements, then you can show that the number of comparisons is n log n, omega of n log n, at least n log n. However, if the model of computation is not necessarily comparisons, you may do something weird. You may design a neural network for all I care, right? So it's not clear whether any model of computation is going to take at least n log n time. Maybe we are all really stupid and we just don't know a better way of coming up with an algorithm that takes time less than n log n. Yeah? But in certain models of computation, like in this one, where the model is just probing, yeah? One probe costs 1 rupee. Now this is a very restricted model of computation, not like any general algorithm like neural networks or something. Here I'm telling you, the model of computation is how do you probe into the memory. Every probe in the memory is going to cost you 1 gold coin or $1 or whatever, right? Under this model of computation, the question is, can you show that no matter what you do, the number of probes required is at least that number? And this is provable. One can prove it. It's a slightly harder exercise, but it is doable. It's not an open problem. And now, suppose 2 crashes was not the right thing, but I ask you, how many probes are enough if you are allowed to crash 3 times? Yeah? Then maybe dividing it into equal parts and this strategy may not be the right one. Both of these, this question is slightly more open-ended. I don't know. I don't know the answer for the second one. But if you have an interesting answer, let me know or think about it or whatever. So that was puzzle 1. So are we ready to go to puzzle 2, or you want a break or some questions? So puzzle 2. So last time I came around the end of the summer school, and people were speaking a lot more from the audience. I think only 2 days of coaching is not enough for... Oh, that was the other thing. Yes, I was not at the end. Okay, doesn't matter. So, second puzzle. So this is not so much of a puzzle, but let's go ahead with it. Okay, there are these constant characters, Akbar and Birbal. They are going to feature in all 3 puzzles. So Akbar is basically a spoiled brat. He is fed up of eating whatever his cooks, master chefs are cooking for him. And he says that to add some variety to my meals, I want my janta to cook for me. And Akbar says that, Birbal, I will eat whatever my people cook for me, but obviously I have some conditions. The rules are as follows. I will announce the set of all possible menu items that my cooks are capable of cooking. Yeah, they could be like chicken biryani and whatever, aloo or tikki or whatever. And there'll be a long list of items. Each citizen can bring as many dishes as he or she likes. So I go with some, whatever, gulab jamuns and jalebis and something else, cakes maybe, and you go with something else, etc. Each of us comes with a bunch of items cooked for the dawat. Now, at the beginning of each meal course, say the starters, Akbar will say, oh, I feel like eating, I don't know, paneer tikka, okay? And then whoever has bought paneer tikka with them will step forward, okay? And then Birbal will say, okay, I choose you. You serve him paneer tikka. But once a person has served the dish, that person cannot serve another dish that day. So suppose I got selected in the first round to serve starters, I serve and I go home. I may have 5 other things in my basket, but I don't get a chance to do that. All right, so that's the set of rules. Here is the problem. We need to serve. Birbal's task is, he needs to keep Akbar happy. So imagine that so I will say more about it, but basically the idea is that whatever Akbar is asking for at any given time, if it's not present among the remaining guys, Akbar is going to be kind of unhappy. All right? So Birbal's task is to serve as many items as possible to Akbar. Clear? The question is clear. Of course, Birbal does not know who has which dishes, right? So that's a problem. So first question is this task even difficult? Or it's something that Birbal should be able to handle? I mean, Birbal is Birbal after all. Is this something difficult to do, or is this doable? Yes. Okay, so fine. I claim that this is not a very trivial task. Let's see why. Suppose Akbar announces that he wants dish D1. Okay? Now there are two people, say X1 and X2, me and somebody else. Both have dish D1. Now Birbal doesn't know what else I have, what else Akbar is going to ask later on. All of this is not something that Birbal already knows, right? So now we are the two people who have this dish D1. He can arbitrarily choose any one of us. So Birbal decides to select X1. Akbar then announces that I want dish D2. Now it could be that X2 is the only remaining guy who doesn't have dish D2, but I have the dish D2, but I have been sent home because I already served D1. One more time, so I'll say this more clearly as well. So X2 does not have D2, however X1 had D1. X1 had D2 as well. So let me just depict it a little bit pictorically. So there is this dish D1, which is with X1 as well as X2. However, D2 is only with X1. So now first Akbar comes, asks for D1, and Birbal decides to let X1 serve D1. Now Akbar is not going to get D2. That's it, right? There is absolutely no way that Akbar's second demand can be met if the first demand is met so. Yeah? What I've done here is drawn a small graph for you. A graph is just a bunch of vertices, which are these blue things, and edges are things that connect these blue things, right? And they are denoted by capital X and capital E, the set of vertices and set of edges. What I'm asking you to find in this graph is a maximum matching. What is a maximum matching? Maximum number of disjoint set of edges in this graph. Yeah? So the maximum matching in this graph is actually D1x2 and D2x1. Yeah? But this matching is being created on the fly as we go along, right? So it's not a matching that is already, the graph is not known a priori. Graph is coming one vertex at a time. So Birbal needs to find maximum sized set M star of edges such that no two edges in M star share an endpoint. That's what he wants to do. And M star in this graph is this. So maximum matching is a problem that is very well studied in computer science, and in fact it has a lot of connections to, if you look at the polytope of all the matchings, that's also a very beautiful mathematical object. It's a convex polytope, and that's a very beautiful mathematical object. There are many properties about it which are studied, which are known, and so on. So there's a whole matching theory related to this. Things related to matching connect to determinants, connect to permanents, connect to other linear algebra that you may have seen in the past, and so on. Okay, so matchings are very beautiful graph theoretic objects, which are also sometimes studied by discrete mathematicians, I mean, the people who study discrete mathematics and so on, combinatorial. And maximum matching problem, as I said already, given a set of vertices and edges, find the maximum sized matching in this graph. So obviously, if you give me a task to perform, my first intuitive thing would be, I'll give you an algorithm. Yeah, because that's how we all think. We have to get around one point of the city to the other. We just try to figure out what's the closest route or so on, right? That's how we think. So if I were to come up with an algorithm for matching, here is what I would do. Yeah, I will say, let's start with an empty set M. Yeah. And as soon as an edge is revealed, I will put that edge into my set M, provided there is no other edge in my set M that has an endpoint being shared with this new edge. Right? I can always do that. So that's what this algorithm is doing if you look at it. M is empty. What am I supposed to do here? Yeah, M is empty. And as soon as an edge is presented, look at all the edges present in M, see that they don't share any endpoint, and if they don't, add the edge to the matching. If they share an endpoint, of course, go to the next edge. Don't do anything here. Keep doing this. Finally, output the cardinality of the set M that you have created in the process. Yeah? It's a very simple, very easy algorithm. Unfortunately, as we saw, this doesn't always give a maximum matching, right? Because if this edge comes first in my, if I consider this edge and I put it, then I have no way to put any edge corresponding to this. So M is the matching that will be formed by the algorithm. Maximum matching, as we saw, is this. M is not a maximum matching, but M does give something. It gives us a maximal matching. And what's a maximal matching? It's a set inside which I cannot add any more edges so that it continues to be a matching. If the set is already a matching, I cannot add anything more to it so that it continues to be a matching. Now, a maximal matching, you may ask, is this good enough? I may not be able to cater to Akbar's all possible needs. Yeah? But if Akbar is willing to be slightly reasonable, can I serve maybe half the dishes that he asks for in this algorithm? Yeah? I mean, that won't make Akbar very happy, but maybe it will not make him very angry either, right? Or hangry, as they call it. But in fact, you can actually get half the edges through this maximal algorithm. Yeah? So the algorithm that we saw on the previous slide actually achieves what is known as a half approximation. Yeah? So if in the best case, you can find the maximum matching of size, say k, yeah? Then this algorithm will guarantee that you get a matching of size at least k by 2. You were hoping for k, but you got at least k by 2. In our small example, it was easy to see. The maximum matching was of size 2. We got a matching of size 1. But this continues. This trend is something that continues. And that's very easy to see why it should be a half approximation. Why is it a half approximation? Well, imagine any edge. Imagine any edge in the graph. Yeah? Suppose this edge was supposed to be in the maximum matching. Yeah? Or let's think about it the other way. Suppose this edge is in the maximal matching. Yeah? Then how many edges from the maximum matching could it have prohibited from being added to this set? One on this side and another on this side. So any edge in this maximal matching that we found prohibits 2 good edges from getting added into this set. So in the worst case, you are at most half away from being that maximum set. Okay? So this is slightly vague probably, but believe me that it achieves half approximation in that it can serve Akbar's half, it can cater to Akbar's half of Akbar's needs. So slightly more realistic situation, and this I think is familiar to all of us, which is called the AdWords problem. So this is a problem exactly again the problem that we saw. And you can Google these keywords if you want. So what is this AdWords problem, Google's AdWords problem? There are bidders. So for example, I am selling shoes. Yeah? I'm no Bata or whatever other Reebok and so on, but I'm a local vendor trying to sell shoes. I could go to Google and say that, look, if anybody anytime looks for running, sports or any such keywords on Google, please show my advertisement on the side. Yeah? So I'm a bidder. There could be a bunch of bidders, Reebok, Adidas, all of them could be bidders. And there are key phrases. So for instance, if somebody is looking for a frying pan, I will say that no, my bid is not on that because I'm a shoe selling company. I don't want to show my ad if somebody is looking for a frying pan, because very likely they won't click on me. Yeah? The other hand, if somebody is looking for running, sports, etc., I want to bid on such query words, and I'll bid on those. So there are bidders and there are query phrases. Okay, that's the two sides of this graph. And advertisers bid on a subset of search phrases, yeah, just like I said. And each search query of users arrives as a stream, right? Because all of us are also users of Google search engine. So we may be, you may be looking for some movie tickets, I may be looking for running shoes, whatever it may be, right? So all these search queries are going in an online fashion. Just like Akbar was asking for various dishes at his whim, we are doing the same to Google in some sense, right? And the bidders can now, as a bidder, as a company holder, I have already said that, look, if somebody looks for these and these query phrases, please show my advertisement. So now it's up to, it's Google's, like in our puzzles case, it was completely Birbal's, it was going to benefit Birbal to show pick the right guy. Exactly in the same way, it helps Google to show the correct advertisements. So it's exactly this problem that Google is trying to solve. And of course, Google is earning humongous revenues by showing such correct ads. So they better design good algorithms for this maximum matching problem, right? They better solve this problem as well as they can. Half is good, maybe not good enough, right? So that's where this problem, that's the reincarnation of this problem in the form of a puzzle. So again, there are very interesting open questions here. So, this is a developing area right now, and there are very interesting algorithms that are being developed. If you just Google search for something like online matching algorithms or something like these key phrases, you will find cutting edge researchers working on this area, not necessarily only from Google, Microsoft, even university professors investing their time on this problem because it's quite an important problem. So, as I said, can Birbal, so this is a question for you. Can Birbal serve more than half fraction of the dishes requested by Akbar? Can you come up with some other algorithm for the same task which serves more than half the dishes? And in fact, some such algorithms are actually known. And as I said, there is always, for every algorithmic question I can ask, there is always a lower bounds question lurking somewhere behind there. Yeah? What is the best fraction that you can achieve? All algorithms have their own limitations, right? So can you provably show that however clever you could be, you won't be able to design an algorithm that satisfies more than alpha fraction of Akbar's wishes, right? So there's this, as I said, lower bound question. This is like a dual world. You come up with an algorithm, then the lower bound person will ask you, but is this the best you can do? And then at some point, the algorithmist will give up and say, maybe this is the best anybody can do. And let's try to prove that, right? So that's the other question you could ask. Both of these are slightly open-ended questions, but if you're curious, you'll find a lot of material about this online. So I encourage you to think about it or Google it or whatever. Okay. So that's the second puzzle. Break, no break, third puzzle. Can I start? Okay. So here is a little joke, but graph theory is good. You want to probably know it. Okay. So the third puzzle, again, as expected, there will be Akbar and Birbal there. The farmer is going to come back actually. So the farmer goes back, he spends his 40 gold coins, they turn out to be not enough. He comes back saying that, Your Highness, 40 gold coins were way too little for my big family. Akbar says, yeah, take what you can, but here are the rules. And the rules have changed a bit. Okay. So again, there are 100 doors as shown, but now they are in a grid. Okay. Opening each door costs only 1 gold coin. There's no distinction between this 40 and 1 and so on. Every door will cost you 1 gold coin. Each door behind it has a hidden number. So you open the door, behind that door somewhere a number is written. And as soon as you find a door such that all its neighboring doors have numbers smaller than it, Akbar will give him 100 gold coins. Okay? So in some sense, you are trying to find a local maxima. Yeah? And what do I mean by neighbors? So suppose I look at this door. Yeah? Then its neighbors are only 4. Namely this door, and this door. The neighbors, we don't count this, and this. Alright? Just a definition for the sake of this puzzle. You could redefine the puzzle with other guys being called neighbors as well. For my puzzle, this is the notion of the neighbor. So if this is a door, these 4 are the neighbors. If a corner point is a door, then these 2 are its neighbors. And something along the edge is a door, then these 3 are its neighbors. Alright? So the definition of neighbor is clear, the puzzle is clear. Good. So again, how much can farmer take home? Let's, as usual, discuss a simple problem. So one very simple strategy is start opening doors one after the other. 1, 2, 3, 4, whatever. Top row, then the next row, then the next row, next the next row, etc. In this situation, the farmer may end up with 0 gold coins, right? Because the last entry that the farmer may check may be the largest guy. Look, for example, in this little example here. Yeah, the doors are numbered 1, 2, 3, 4, etc. You start opening them row wise. 1 is not a local maxima, 2 is not a local maxima, 3 is not, etc., etc., all the way up to 16, which is the only local maxima in this. Right? So this is a bad strategy, clearly. What is a possible good strategy? Now I'm going to just halt for a minute or two. I'm going to ask you to think about it and tell me if you come up with something. So now this is something you have to do online. Any door, yeah. Any door. Okay, one little question is, what is the minimum farmer may have to pay? I mean, unless he is lucky, he'll just open the first door where it's a local maxima. But even to figure out that something is a local maxima or not, yeah, for the worst case input, he may have to open at least 5 doors. You're getting me? There is one lower bound we can say in this particular question, that at least 5 gold coins will have to be paid. Or all the 4. Akbar is not going to give that information for free. True. So that's not the worst case analysis. What you're saying is right. It could be that there are inputs where he'll end up paying only 2. If it's the corner, one of the 4 corners, then he'll end up paying only 2. But that's not worst case analysis, is it? You could move across the diagonal, but is that your strategy? Very good. Okay, so what is being presented over here is sort of a divide, conquer type strategy. What is being suggested is, you look at the diagonal, open all the doors above and below the entries of the diagonal. You will end up paying in a n cross n grid, you will end up paying something around 4n or 3n or something like that. But it's not n square, right? We were paying n square earlier. But having opened some 3n or 4n doors, what is the information you've gained from this? Have you made any progress? So suppose you figure out none of them were local maxima. This could happen. So it's not just that you're opening the doors and figuring out the middle guys are not maximas. You also know a little bit about the doors above and below. Absolutely right. So then from there, can we conclude anything? We should be able to, logically. We've got some information, we should be able to, but what is it that we can conclude?
Suppose I have a block and I go into it and I have to pay money, then I can tell that it is not the local maximum, then I can go to the next and to the next. So if suppose not all of these are not local maxima, then there is a chance that the blocks surrounding them are local maxima. Then I can check them in such a way that a trap is formed, so one of them has to be the local maxima.
So look at this example. Let's try to see if your strategy works. And imagine this is not a 4x4 grid, but like a n×n grid. Yeah. Somewhere in the middle you start, you open that door and 4 of its neighbors, you figure out it's not a local maximum. You got some information, namely, there is some larger number sitting above it, some smaller number sitting below it. Suppose you continued this process. Yeah. In the worst case, again, you might end up opening all the doors one after the other. If the strategy continues to be this same thing. Yeah. Whatever other, like a Minesweep, I don't know how many of you have played Minesweep. Maybe it's still a mobile game, right? Is this a mobile? Oh, it's a computer game still. Okay, good to know. So what happens in the Minesweep game is that you click on something hoping that it's not a mine, then a bunch of area opens up, then you see a 1 and then click around it and so on, right? So you could do that. That is what similar strategy is being suggested. Unfortunately, you will be able to argue, maybe with some more time, that this is also going to be in the worst case like a n² type strategy. You may be able to do something like n² / 4 or something, which is not terribly bad, but it's still kind of n². So always, I mean, maybe I should not say always, but sometimes when you are stuck at a problem, you don't know how to solve it, simplify, right? That's the best we can do. We don't know how to solve the current problem. Okay, let's look at a simpler version of the same problem. So I needed to say, yeah, this divide and conquer middle row, I had a middle row instead of the diagonal. I wanted to say that if you try to work out this strategy, it won't quite work. But let me not spend time on that right now. Okay? So let's go to this point I was trying to make earlier, which is that if I don't know how to solve the problem, really, then it might help to look at an easier version of the problem. This is probably a rule of thumb all scientists more or less use in their work. So why not with this puzzle as well, right? So now the other message I'll give through this puzzle, which is that instead of looking at a 2x2 grid, look at a single array. This is not a rule you should apply in mathematics though, because some things happen very weirdly in smaller dimensions that don't carry over in the higher dimension. So don't take this message back. Definitely take back the message that you should try to simplify whenever you don't know how to solve a very hard problem. So let's look at, instead of on a grid, these doors are arranged in a single line. Now, can we do something? So again, I'll pause for a bit, let you come up with some answers. How much time do I have? Like 5 minutes or 5 minutes? Probably a bit unfair to ask you to think so much at the end of the day, but I hear there is a problem solving session after dinner too, so. Huh.
Say I start the first door,
Huh.
then if it is not the one, then I skip one door and then take the next door.
Okay.
If it is not the one.
So two strategies are emerging. One is, sorry, another one? I think the two strategies there are the same. Okay, so let's look at them one after the other. One of the strategies that was being suggested is open the first door, skip the second one. Open the third one, skip the fourth one, etc. Now,
Still, in the worst case,
right, good, very good. So in the worst case situation, such a strategy is still going to be n or n by 2 or whatever, n actually. Yeah, because the doors you open give us no information about it. So what we are hoping is the first and the third door have some small values. Say in the best case situation, there were 1 and 2 numbered. Then we know the middle door is 3, right? So we are in very good shape. And probably by opening about half of the end doors, we may be able to locate two really large numbers, two really small numbers such that a larger number better be between them. But this is if we are very lucky, you know, and by Murphy's laws, we are not most of the time. So this is not going to work. What was the other strategy again? Right. Beside it, very good.
So either is bigger, like if the center number is bigger than both of them,
Then you are done. Very good.
if the right side number is bigger, then we open the door next to it.
Okay. Okay. So here is another strategy that is emerging. Maybe yours was slightly different, no? Same thing? Same thing. Sure? Okay. So, okay, the strategy that is being suggested is you open the middle door and the two door next to it. Pay 3 gold coins, whatever. Now, best case situation, which is not going to happen to us, I guess, but best case situation is the two doors next to it were of lower value than the middle door, then you are really done. If not, there is one of which is higher than this. Now her suggestion is then the local maxima better be on that side. Yeah. So now open each one of them. Now in the worst case, how much will this cost if there were n doors? N by 2 plus 3, I guess, or I don't know, n by 2 plus 1. Yeah, n by 2 plus 1. This is how much it will cost. Yeah. Can you do better than that? I just am so annoying. I keep asking, can you do better than that? Can you do better than that? But you can, let me tell you that. Can we take the square root here? Can we apply puzzle 1 strategy over here? Good idea. Can we? Yeah, exactly, right? Because there, it made sense to kind of divide it into because it was a search question we were trying to look for. We knew that from a point on, it had a certain property and before a point, it had a certain different property. We were trying to locate where that shift of property happens. Here on the other hand, the numbers could be all arbitrary, right? So, not clear. But you've almost come to the solution. Huh. Okay. Fantastic. So what did we analyze and say about the strategy that was the first one that was suggested? Sorry, I need to know your names at some point. Soumya and Pragya. Okay, great. So what Soumya suggested was that every other door, right? But in the worst case, we saw this takes n. So now if we combine this strategy with the n by 2 strategy, it's still going to take n by 2 in the worst case, isn't it? Because you'll open the middle and 3 others, then skip every other and do. But then skip every other and do in any range of range k takes worst case k. So it's going to take n by 2 plus 1 still. Yeah, so not quite yet. So we are not within the realms of the ideas which will take us to the best solution. You are taking linear combinations of them. That's not working out. So we have to go out of the space. So what is the next idea that you can perform? One excellent observation that came about through Pragya's, can I take 5 more minutes? Sorry. So the excellent observation that was made was that I open the center door, 2 neighboring doors, and if the center is not the maxima, then one of the doors is larger than it, and in that direction, we will find a local maxima. Is everybody clear about this correctness of this statement? Yeah? It's not going to happen that the middle number is say 5, one of them is 17 and another is 3, and I go in the direction of 70, I will never find a local maxima, right? Because if I have a 5 in the middle, 17 next, and I keep going, yeah? And at every point the number keeps increasing. That means none of them are local maximas, but then the last one must be, yeah? Or else there is a local maxima early on. So it is the case that it is true that if the middle guy is not a local maxima, we have found a region of length n by 2 where there is a local maxima. So what did we do exactly then? What we did here was, we had a problem on n elements of finding a local maxima. By probing 3 things, we figured out, we came to a smaller problem. What is the smaller problem? Finding a local maxima in a range of n by 2. Now can we recurse? This is called recursion, right? You have a range of n elements, and the problem to be solved is find a local maxima. By using 3 probes, yeah? So imagine the total number of probes required for n elements is something. We don't know what that is. What we do know is, this quantity is, I pay 3 probes and then recurse, right? So the amount that I need to probe, or the number of times I need to probe, can be written down. I'm sorry, the ink is really, you can see it? Okay. So, you know, this recursion is, this is what we are saying. And now if you solve this recursion, what do you think you get? Solve this for n. By that I mean P of n equals 3 plus P of n by 2. But now apply this to P of n by 2. So it's 3 plus 3 plus 3. How many times? Till the point n by 2 to the I becomes 1 or 0. So how quickly will that happen? We want n by 2 to the I to become like 1. Then it should be like log to the base 2. Right? Just by solving this, you see that I better be log of n to the base 2. Yeah? So what this is telling us is that if you do this log n many times, then every time paying 3 gold coins, that is 3 times log n many gold coins, will be paid to figure out where the local maxima is. Everybody clear about this solution as well? So this is called binary search. Yeah? This is exactly what a binary search in an array is. Yeah, you want to find if it's an array sorted already, then you can actually find the exact element in that array. In our case, the array is not quite sorted, so we are only able to find a local maxima or local minima similarly, right? So this is basically binary search applied to finding local maxima. So this is what this says. The only thing that one needs to convince oneself is there must be a local maxima to the left of the middle door if the larger element was on the left in the middle probe. And that is something I think you can convince yourself of anyway. So overall, how many gold coins? So you can do a little bit of math, log of 100. Actually, log of 100 is not quite correct because it should be 3 times log of 100. And then, yeah, so this calculation is not quite correct. It should be 100 minus 3 times log of 100, which is what the farmer pays. Whatever is left over is what he can take home. Okay. Now still the question of n cross n grid remains. And now if you Google this, finding local maxima in a n cross n grid, you will find a solution for this. There's no fun in that, I believe. So if you want to solve this question, you have to solve this question where the number of probes, again, is n. Not exactly n, maybe 10 times n, or order of n. They shouldn't be n square. Can you do that? Okay. So a slightly more realistic situation. You are given a height altitude map for a certain region and you want to figure out where should I dig a well, or where should I find whatever, the right place to dig a well or whatever. Yeah, so this could be one possible. So figuring out local maxima, this is a problem that even Google Earth and whatnot, they have to solve. They have to solve other problems as well, just from images, figuring out what is deep, what is not, and so on. But once you figure out what are the local maximas, what are the local minimas, how if we turn the course of a river, where will it flow, and stuff like that. Strategy planning. Or you are an ice cream vendor and you go to Goa to sell ice creams for some reason, then you can figure out where to put up your ice cream stalls on a hot day, like today, and so on. So that's about it. These were the 3 puzzles I wanted to discuss. With that, I would like to stop. Again, slightly in jest, but maybe one of you will start an Indian Google going forward. So you should pay attention when you're doing all the abstract math, that does it model interesting questions? Keep an eye for interesting questions and see whatever tools you know, are they applicable anywhere? This is always fun to do. This is always a great way to build your set of tools as well. Also learn how to translate real life problems into equivalent mathematical problems. Often, real life problems come with so many different demands, and rather than paying attention to each one of them, figure out what are the important ones. Does this correspond to any mathematical problem? Observe that there is a deeper problem behind every improvement in a real life problem. So when Google comes up with a certain algorithm, there is some deeper math going on there's some deeper thought process sometimes, hopefully, there. And also, of course, like your math background is anyway going to teach you going forward, but you have to get your hands dirty as well. So all this is good, fun, and so on, but at the end of the day, you have to get your hands dirty. You have to be good at your stuff first. So learn the tools well. This is just a word, what is it called? Word cloud, no. Something for combinatorics and so on. So, yeah, thank you.